Welcome to the 14th lecture on computational mathematics with SageMath. Now onwards we will start using SageMath and we will explore mathematical concepts using SageMath. So I hope all of you have managed to install Sage in your system, or at least you have figured it out how to use it online. In case you have problem in installing in your system, you can use it online, that I explained in the last video. So let us get started. I have already installed in my system, and in my system it has created three icons on my desktop. One is SageMath Notebook, another one is SageMath 9.1, another one is SageMath Cell. So we will be using SageMath Notebook. So let us double click on this, and once you double click, it will start SageMath server in a Jupyter Notebook. Initially it may take a little time, but subsequently it will be faster. So this is the local host for SageMath server. You can see your files, directories and all other things, etc. So let me go to one directory which I have created as NPTEL lectures. So if I click on this, there are files which we created last week. So now let us go to new and click on new. In case you want to just do Python programming, that also option is available, so you can click on Python 3. We will be using SageMath 9.1. so let us click on SageMath 9.1. Once you click SageMath 9.1, it will create an untitled Jupyter Notebook. So we can rename this. So let us rename this. I will call this as computational mathematics with SageMath, and let me say this is lecture 3-1. Okay. So that's the name I am giving to this worksheet. So by default it will create the extension IPYNB, that's the Jupyter Notebook default extension. Okay. Now this is where you can type all the commands, and you can run this exactly in the same way as we did when we wrote Python programs using Jupyter Notebook. Okay. So this SageMath, as I said in the introductory video, is very useful, and you can explore most of the mathematical concepts using SageMath. Okay. So let us get started. Suppose we want to, let us say, explore integers. So how do we do that? We will define, let us say, n is equal to some integer, let us say 7642, 7642. So let us store this. Now when we have created n is equal to 7642, actually n is an object of integer class. So if I ask for what is type of n, it will tell you that it is coming from Sage ring integer and integer. Now all the methods that you want to apply on n can be obtained using .tab operator, because this, as I said, this SageMath is Python based, so all the functionality of Python will also be available here. So if I say n dot and then press tab, you will see all the methods that can be applied to this object n. So for example, you can go through this list and explore maybe a few of them. So let us see, suppose we want to look at this integer, and I can ask whether this integer is prime or not a prime number. So of course we know that this is even integer, so it cannot be prime. So but still we can check whether it is a prime or not. How do we check that? So if you again press the tab, you will see an option. There is an option called is underscore prime, and then you give this empty parenthesis, because this is a method. You want to access this method known as is underscore prime from this integer class, and you want to apply on an object n. So, this is what you have to do. Okay. So, this says that this is not a prime number. Okay. So, if it is not a prime number, you can ask various questions. So, for example, I can say n dot factors, n dot factor. So, what are the factors of this? So, it says that it has only 2 factors, namely 2 and 38 21. You can ask for n dot next underscore prime. So, that will give you a number which is prime and it is immediately after this. So, let us run this. It gives you 7643. So, it was 7641 42 and the next number, next integer is a prime number. So, that is very nice. So, you can see here for example, next prime or is underscore prime. First of all, is underscore prime checks primality of this number n. So, whenever you want to check something, let us say you want to check whether some integer is even or odd, or check prime, not prime, check a matrix which is singular, non-singular, etc. Generally, the name of the method will start with is, and since it is combination of is and prime, a general philosophy in SageMath is to combine these two using underscore, and in some other software it may be some other philosophy, but in SageMath 2 keywords are combined to make a single method or function using underscore. Okay. So, this is the next prime. If I say n dot, if I want to find previous prime, I can say pre, and you can, after typing let us say pre or just pr, you can press tab, then it will show you all the options that can exist with 2 characters pr. So, there is an option called previous prime. So, if I just use previous prime, you get this previous prime which is 39. So, 39 and 7639 and 7643 are 2 consecutive primes. Okay. Similarly, you can ask for, let us say, divisors. We already found out factors, but if I say n dot divisors, then it will give you all the divisors of this, so including 1 and the number itself. So, all the divisors it will give you. It will give you divisors in case it is repeated. For example, if I say divisors of, let us say, 8. So, divisors of 8 are 1, 2, 4, 8. So, it will give you only the divisors as a list, right. So, you can see here n dot divisors can be used, or we can use divisors in the bracket n. Both are the same thing. So, divisor is also a function, at the same time it is also a method inside integer class. Okay. So, next let us say we want to find out how many digits are there. So, you can say n dot, and if I say digit, n dot digits, then what will it create? It will create a list of digits. It will separate all the digits and create a list. So, and it will start with units place. So, 2, 4, 6, 7, our number was 7642. So, you can separate the digits starting from units place onwards, and you can count how many digits are there. I can say that len, length of n dot digits, will give me number of digits. So, it has 4 digits, and you can work with any big number. So, if I say, let us say m is equal to some large number, and then if I ask for what is m dot digits, then m dot digits, then it will separate all the digits, and you can count the length. However, you can find the length of digits, length of or number of digits in an integer using another option called n dot n digits. So, if I say n digits, it will tell me number of digits. So, for example, if I say m dot n digits, it has 14 digits, and that is what it gives me. Okay. So, so once you have defined an integer, any integer, you can check various things about that integer, like whether it is prime, if it is not prime, what are factors, next prime, previous prime, all these things using dot tab operator. So suppose you want to, for example, find out any about any function. So for example, if I have said divisors, so if I say n dot divisors, and you can put either help, you can write help, inside help you can write divisors, or you can say this is 1, or you can even say n dot divisors, just one second, n dot divisors, and put a question mark, then it will open a help document which is inbuilt. Just to tell you, in case you are opening this first time, it may take a little time, but subsequently it will be faster. So you can see here it tells you that return n dot divisors returns the list of all positive integers, divisors of this integer, and sorted in increasing order. So after finding the divisors, it will sort in increasing order. That is what it means, and it gives you several examples, and you can even copy paste any of this example. For example, if I can just copy paste this, let me make it bigger so that it will fit in one of this tab, and I have copied this, I can paste it here. So it will all these things, when you open this help document, this you can go through this, and then you can make use of any of the syntax which are there in this help document. So in the beginning, it is a good idea to actually find out help or take help on every function that you utilize. It will, and you can go through, it will tell you what is this function, how it works, with several examples. Okay. Instead of one question mark, if you write two question marks, so if I say n dot divisor and double question mark, then also it will open a help document, but it will be more detailed help document along with the source code. So this is a function defined, and it tells you how it has been defined along with the examples, and you can see here how this program has been written. So that is what I meant by saying that SageMath is open source software. So not only you can use it freely, but you can also see the source code, and you can even modify the source code. Okay. So right, so this is how you can take help on any function or method. Okay. Now suppose you want to have two integers. Let us say define two integers a and b. So I can say a comma b is equal to, again let us say 7 6 4 2, and another integer b is, let us say 63. So a and b are, you can print what are a and b, it will tell you a and b are this. Okay. Now suppose we want to check whether this number a is divisible by 63 or not. So one way is to look at look at a divided by b. When you say a divided by b, it tells me that actually it gives me the same integer by this. So therefore it is not divisible. Actually this returns a rational number. In case there are some common factors, it will get rid of these common factors. So for example, if I say 20, let us say 38 divided by 12, then it will give me 19 by 6, because it will take out this factor 2 from the numerator and denominator. Okay. So this is how you can define a rational number. In case you wanted to find, let us say a divided by b as a real number, you could say, for example, 38 divided by 12.0, this is one way, or I can also say 38 divided by 12 and then press dot and n. This dot n means it is going to give you this give you numerical values. So there are two ways in which you can find the numerical values, but dot n we will keep using in order to get numerical value of any variable. Right. So we have defined two integers a and b like this, and suppose we know now that this a is not divisible by b. Let us change instead of 63 3, let us say B is 62, and now we want to check whether A is divisible by B or not. So, how do we check? We can say, of course, we can still say A double slash B or A for double forward slash B, and then we can check what is the quotient. So, quotient is 123, and we can find out remainder A percentage B, that will give me the remainder. So, remainder is non-zero, therefore, this is not divisible. You could also find this by a command, let us say B dot divide, V dot divide divides A. So, it will tell you whether B divides A or not. So, either you can find quotient remainder, or you can check whether B divides A using this function. You could find quotient and remainder by double slash and percentage, but there is also a inbuilt function. So, if I again, for example, if I say A dot and press tab, and let us just explore this list, and is there something to find quotient and remainder. So, if you go down to Q, so P Q here, yeah, there is one called quotient QUO underscore RAM, and in the bracket if I say B, it tells me the quotient is 123, remainder is 16. So, I can store this into, let us say, Q comma R is equal to this, and we can even verify B into the quotient plus remainder, is it equal to A? The answer is yes, right. So, this is how you can find quotient and remainder. If you have two integers, you can also find, for example, GCD of these two integers. So, if I say GCD of A comma B, it will tell me the GCD is 2. You could also have said A dot GCD and in the bracket B, both are same. So, it can be used, GCD can be used as a function or as a method. Okay. Instead of finding GCD, if you say X GCD of A comma B, it will return three things. First one is GCD, and this is, let us say, let me call this as X and this is Y. So, these two integers X and Y have the property that X times A plus Y times B should be equal to this GCD. So, GCD can be written as linear integer linear combination of A and B. This is what is called Bezo's identity. Given two integers A and B, and D, if D is GCD of A and B, then there exist integers X and Y such that X times A plus Y times B is equal to GCD. So, let us verify that. How do we verify that? Let me store this the output in D, which is GCD, and X, that is the first integer, and Y, second integer. Now, you can print what are D comma X comma Y. It will tell you this. Now, if I verify X star A plus Y star B, is it equal to D? We should get answer true, right. So, this we have verified Bezo's identity, right. And the beauty of the Sage is that we have used, for example, GCD function, and you know that you can also find GCD of polynomials. So, the same function can be applied to find GCD of polynomials, and in this case GCD of integers. So, that is another advantage. Let us also look at, let me again define an integer n, which is somewhat, let us say, big integer, let us say this n, and suppose we want to find out how many primes are there between 2 and n. Okay, how many primes are there between 2 and n. So, if I say there is a function called prime underscore pi, which will find the number of primes, and if I say in the bracket n, this tells me that it has so many primes between 2 and n. So, you can count how many primes are there. For example, if I say tell me the integer n such that 2 to n, between 2 and n there are 1000 primes. So, what is that integer? That very simple Python code will tell me how to find this. So, for example, you can even find out how many integers are there from 1 to n which are co-prime to n. So, there is a function called Euler Euler phi, and if I say Euler phi 30, then it will tell me this is 8, which means that there are 8 integers between 1 and 30 which are co-prime to 30. And how do we find this? So that means there are 8 integers such that integers and 30 GCD of these two are is 1. That is what is we mean by saying co-prime. So for example, I can say k for k in range 30, so it will give 0 to 30. I want including 30, so I will say 31. And when you take this k, if GCD of k and 30 is equal to 1, then these are the integers. Now you can count what is the length of this, so you can say len of this, it will tell me this is the 8. So we have not only found out this number of integers which are co-prime to 30 using inbuilt function Euler phi, but we have also verified this using this. So and these are all Python codes. So you can see here any Python code we can run as it is, right. So you can also find, for example, we have found GCD of 2 integers a and b. Suppose I want to find GCD of 3 integers, let us say a, b and c. So let us define a comma b comma c is equal to, let us say 76, 98 and 392. And if I want to find out GCD of a, b and c, let us run this. It says that we cannot find because it takes only 1 to 2 position. Therefore, we cannot find GCD of 3 integers at a time. But what you can do is you can find first GCD of a and b, and then the GCD of a and b, and then find GCD of c along with GCD of a and b. So we will say GCD of a and b with c, that is 2. So 2 is GCD of these 3 integers, right. So this is how you can explore any integer and look at various properties of. So and SageMath is actually very good in number theory. The inventor of SageMath, Professor William Stein, is himself a number theorist. So you can expect this to have lot of functional facilities when it comes to number theory, and that's exactly what is true. Okay. Next, let us say we want to look at some other function that we know how to deal with. So for example, if I say let us say n is equal to, let us say 1475, okay, and I want to find factorial of this number. So if I say n dot factorial, it will tell me the factorial of this 1475, and there are so many digits in fact. So you can even, let us store this what we have found out in a number. Let me call this as number as capital N. Capital N is equal to, you could also say factorial instead of n dot factorial n, right. And suppose we want to find out number of digits, I can simply say capital N dot n digits, it tells me the number of digits are 4036, and if I want to find out how many zeros are there, then what we can do is we can say n dot digits. So it will separate all the digits, and then let us store this in capital F, and then we can say f dot count, and then count 0. There are 700 zeros in 1475 factorial, right. So that is quite easy. You can also apply various scientific functions like sine, cosine, exponential, logarithmic, and all these things are inbuilt. So for example, if I say sine of 3 radian, it just returns sine 3. If I want to find the numerical value, there are two ways in which we can do. We can say sine of 3.0, or we can say sine 3 sine 3 in the bracket and then dot n. This is to find numerical value, right. So, that is how we can find. Suppose if I want to find out square root of, let us say 7, this returns just square root of 7. In fact, you can ask it to show in symbolic notation. If I say show sqrt of 7, sorry, sqrt of 7, then it will just print square root 7. If I want to find numerical values of this, by now we know what is to be done. This you can say 7.0, or you can say sqrt in the bracket 7 and then dot n. You can even print how many digits do you want. So, for example, if I say this, and in the bracket if I put digits is equal to, let us say 50, then it will give you so many digits. So, that option is also there. And as I said, this any Python program you can run inside this Sage notebook or Sage worksheet as it is. So, for example, if I say import let us say import numpy as np, then it will import numpy, and after that so it is still doing, right, it has done star. If you see star here, that means the kernel is still running. Generally, I find SageMath in Windows is a bit slower compared to SageMath in Linux. Now, for example, in numpy you have a function array. So, if I say npy dot array and then I say 1 2 3 1 2 3, it will create an array. Or if I say np dot lin space, all these things we have used, between let us say 5 and 10 I want 100 points, then this can be also used. So, all these things are very easy to explore, and generally it is actually much better than using Python. Of course, behind the scene Python works, but many things have been simplified in SageMath, and that is what we will see as we go along. So, at the end, let me leave you with some simple exercises. So, you can try these exercises, which will actually kind of test whatever things that we have done in this particular session. So, let me just convert this into Markdown, and let me just bring the list of exercises, which just copy paste this. Yeah, so these are some exercises you should try. So, for example, find GCD and LCM of two integers and check that multiplication of GCD and LCM is the product of the two numbers. You can just check whether the Bezo's identity can be extended to three integers a, b, c, d. You can find what are the factors of sum of digits in 1275 factorial, and the next one is find out number of co-primes between two integers 62 and 766, and similarly this I already said, you can find integer n such that the number of primes between 2 and n is 10,000, and the last one is to deal with Euler 5 function, which I already told you, but this is you can explore about 562, and you can look at what are the properties of this Euler 5 function. If you are interested, in case you have not done some course in number theory, you can look at let us say Google help about Euler 5 function and try to verify some of the property. So, thank you very much. In the next lecture we will see some more things in SageMath.